Hello and welcome to this practical guide to performance-conscious Python. My name is Robben Migacz and I work with the User Services Group at the University of Utah Center for High Performance Computing. This is a presentation I originally gave at the Rocky Mountain Advanced Computing Consortium High Performance Computing Symposium in 2026. The content is identical. I open with a question here. Why should we care about Python performance? Or isn't performance-conscious Python an oxymoron? And this, to me, is a fair question to ask because, especially in a high-performance computing environment, the languages of choice tend to be low-level languages that are compiled to machine code and have really great performance. So you'll often see scientific software written in C, C++, or Fortran. But you are increasingly seeing software written in Python and other high-level languages, but particularly Python, especially with the increase in machine learning utilization across scientific disciplines. And I think that performance-conscious Python is not actually an oxymoron. I think it is important. And I list 3 reasons here. So first, the performance characteristics of Python are not always intuitive. So this presentation is motivated largely by an interaction I had with a researcher. This researcher had a Python script that was taking too long to run. So in this case, there was a small test that was taking 28 seconds to run. And this script had an algorithm that was actually ideal for running in parallel, for doing multiple things at the same time. It is what we'd call ideally parallel or embarrassingly parallel. And so this researcher, with this knowledge, after we'd met, went to write part of this script to run in parallel. And it was a correct implementation. It gave the correct answer. Again, this was a problem that could be parallelized very easily. And we found this surprising result that it took much longer to run in parallel than it did in serial. That means even though we're running multiple calculations at the same time, it was actually slower than doing them sequentially. And we'll talk a little bit about what happened in this specific instance later in the presentation. Now I have another motivation here, which is that the Python ecosystem is complex and ever growing. So you're rarely writing just Python. You're often working with additional packages that other people have written. These packages may be implemented in lower level languages, which we'll talk a bit about. But the Python ecosystem just continues to grow, and there's innumerable packages and innumerable ways of installing those packages. So I think this is also an important consideration when talking about Python performance, is that oftentimes it's not just the scripts you're writing, it is the tools you're using with your scripts. And I have a final motivation here, which is that Python is widely used, particularly among users who are new to HPC. So I give a little diagram here, a bar chart of the IEEE spectrum ranking of top programming languages in 2025, and Python is number 1. So these look like normalized values to me, and the second language here is Java, but it's less than 0.5 for Python's 1. So I don't know exactly how this metric is calculated, but certainly I would agree that Python is used very broadly across scientific disciplines, but also in industry. Now there's also the 2025 developer survey from Stack Overflow, wherein Python is the number 1 language among respondents in the learning to code and learners that use AI categories. So this again goes to the new to HPC qualification for users running scientific software or writing their own scientific software. Oftentimes they're not starting by learning C, C++, Fortran, any of these low-level languages. They are learning to work with Python, particularly where machine learning is concerned, because there are a lot of machine learning packages in Python. So with this context, I want to move into some essential background knowledge for this presentation, which is that Python is a glue language. And what we mean by that is that when you write Python, the Python code that you're writing could actually be gluing some various components together. So I say over here C extension module, we'll talk a little bit about that. But I want to focus first on what this example here is. So I have an example, import NumPy as NP. We're then creating a NumPy array, and then we're multiplying that array by an integer. Now this is a Python script. This whole thing is a Python script. That's what I have this curly brace for. It is in a single file generally that is going to be interpreted by the Python interpreter. So you're writing Python, but behind the scenes, this numpy.array function here is actually implemented in C. So the developers of NumPy have implemented this in a C extension module. And then when we multiply a by 2, this again, a is a NumPy array. When we multiply a by 2, that is going to trigger a method in Python. If you're not familiar with how this works, we talk a little bit about this in the Introduction to Python series run by the CHPC. But a times 2 is going to trigger the method a.dunderMul, 2 underscores mul, 2 underscores 2. And this function here is similarly implemented in C. So even though we're writing Python, once this actually gets evaluated by the Python interpreter and it goes through this step of being, I guess, transformed into this notation of having the object and then the method mul, dunderMul, that function for a NumPy array is implemented in C. So when we say that Python is a glue language, we often mean that the Python that you write is gluing a bunch of these low-level language components together, like these NumPy universal functions. So with that in mind, Python scripts exist on what I'd call a performance continuum, where the performance characteristics can vary significantly. So on the one end, toward the left here, I consider scripts where most time is spent in optimized packages. So that would be things like NumPy. And then on the other side, there are cases where most of the time is spent in the Python interpreter itself, so not in these lower level packages. So the way this diagram works, it's a kind of confusing Sankey diagram here, is that I consider like the full runtime of the script to be at the top of the screen, and then that can split off into either things that are run in the Python interpreter or things that are run as these lower level packages. So the greenish tinted part here is like saying that every operation, all of the time in your script is spent in the optimized packages, and the yellow is where all of the time is spent in the Python interpreter. And you can have anything in between as well, depending on how much of your script is running on these lower level optimized packages and how much of it is running on the Python interpreter, just pure native Python. Now, most scripts that new users write are going to be toward the right side of this diagram. So they're going to be running mostly pure native Python, whereas a lot of optimized scientific software is on the left side of this diagram. So things like NumPy, SciPy, Pandas, Polars, all of these low-level packages, also things like the machine learning packages. These are highly optimized, and they're going to be running some lower-level languages behind the scenes. So some machine code, in essence, that has been compiled from a lower-level language. Now, this distinction is important, and similarly, profiling your scripts to understand performance characteristics is an important first step for optimization. So you never want to start trying to optimize your script without first understanding what it is actually doing and where it is actually spending most of its time. So I would encourage you to try profiling your programs, your scripts, to see where they're taking the most time and therefore where you have the most potential to improve the performance. Now, I said that the distinction between spending most of your time in the optimized packages and spending most of your time in the Python interpreter with pure Python is important, and that's because how you approach your performance optimization is going to depend on where in that continuum you find yourself. So if you find yourself mostly toward the left side of that continuum, so in the mostly optimized packages regime, I say here, then your options for optimization are actually quite limited. So optimizing your Python scripts themselves won't help much because your Python scripts are offloading much of the calculation, much of your effort, much of your time to these lower level packages. So consider using packages that are optimized for your system, or also consider revisiting your approach to the problem if that's not going to help much with your performance. So I underlined your system here because oftentimes when you're downloading packages for Python, you're getting a pre-built binary package that is generally built for older hardware. This is a compatibility measure. So these are built for an older C standard library and also for compatibility with older CPU instruction sets. So for older hardware. Now, if you're building packages yourself from source, again, these are often implemented in lower level languages where you would need to compile to machine code. If you can do that on your system with the knowledge of the CPU architecture that you have, you can get significant performance improvements in some cases. So I have a quotation here from a recent Talk Python to Me podcast episode from April 2026. And the quotation is, "The difference between the 2009 hardware features and the 2019 or 2023 ones could be a factor of 10x, 20x in performance depending on what you're doing. You can get massive performance increases with these optimized builds." Now, in practice, I don't necessarily agree that you're going to see 10 to 20 times performance increases just by building a package from source. And particularly, I would note that some packages already have features like a CPU dispatcher that are going to help run optimized software on your system. But I think there is truth to this, and I certainly believe that you could see performance improvements on the order of 10 to 100%, and sometimes I think this is true as well, 10 to 20 times, just depending on the software and the nature of what it's actually doing, and whether using more modern CPU architectures or a more modern and optimized C standard library can confer a performance benefit. So this is certainly a consideration if you do find yourself in the regime where you're running already mostly optimized software. You should ask yourself, is that software built specifically for my system, or am I running something that's targeting hardware from 2009 or 2014 or thereabout? Now, on the other hand, if you find yourself on the right side of the continuum from earlier, that's where you're running mostly pure Python with the Python interpreter, you're not spending most of your time in these optimized packages, then you have more room and more options for your optimization. So that's what I actually want to focus on in this presentation moving forward. Now, the first thing might sound kind of silly or overly simple, like show me the packages that will improve the performance of my Python, right? But actually, I think it's useful to take a step back and just ensure you're using a recent version of Python and following best practices. So there's no magic answer here. Just consider using more recent software and following the best practices when you're writing your own software. Now, why do I say use a recent version of Python? Well, new versions of Python don't just get new features, they also get performance enhancements. So this is a quotation from a JetBrains blog post. 48% of people are currently using Python 3.11. This is from August 2025, but also I think this is probably still in the ballpark. I think that's probably not far off from where we stand today. But of these people using Python 3.11, upgrading to 3.13 will make their code run about 11% faster end-to-end while using about 10 to 15% less memory. And if they are one of the 27% still on 3.10 or older, their code gets a whopping approximately 42% speed increase, and memory use can drop by about 20 to 30%. Now, I think that a lot of people who are using 3.10 or older, these are relatively old versions of Python, they might be using the operating system version. Like if you have a Mac computer currently in 2026, the version of Python that ships with your computer is 3.9, and so you are certainly using an older version of Python. But I think there is truth to using a newer version of Python will improve the performance of your scripts generally across the board. So that's why I say start there. It's fairly easy to download a new version of Python. You don't have to make any changes to your software whatsoever. Now, I also mentioned following best practices for your software development. So in my mind, that's things like pre-allocating memory for objects that grow. So if you have a list in Python and you're continuously adding to that list, Python is having to go search for available memory, reallocate the memory. That is a slow operation. So if you're growing some object in memory, pre-allocating some memory for that will really help with performance. Now, another common area where you can improve performance fairly easily is by moving loop invariant statements outside of the loops. So if you're running things multiple times in a loop where you don't necessarily need to do that, you're just wasting cycles. So this is sometimes called hoisting, and don't underestimate its effect. This can really improve the performance of your scripts. Now here's another one where you can cache results in Python and also attribute lookups where feasible. So this is kind of similar to the previous one. These are both following the theme of don't run things more than once if you don't have to. So I would consider these suggestions helpful, or at the very least not detrimental, even if you are later using some optimized scientific Python packages. So I would consider this to be time that is not wasted, even if it doesn't have maybe the most significant effect on performance. Now, the big question for Python performance is about running these lower level packages, these packages with optimized software. So can you use packages optimized for numeric computation? And by this, I mean things like NumPy, Pandas, PyTorch, SciPy, Polars. All of these tools and more are tools that are really going to help with the performance of your scripts. And some of your most significant performance gains will come from using optimized packages. So really my advice here is don't write Python to duplicate the effort of an existing performance-conscious package. If there is a package that someone has put in a lot of time and effort into creating something that runs quickly, that uses maybe less memory than another implementation, by all means use that solution so that you don't have to recreate the wheel. Now there are a few various topics that I'd like to discuss here. I'm going to focus on two, which are the NumPy ecosystem and just-in-time compilers. And I'd like to start with the NumPy ecosystem. So NumPy is the de facto standard for numeric computation in Python. It can really help with the performance of your Python scripts because it gives you support for consistent data types. You're not having to determine the type of things at runtime. It gives you support for contiguous memory, vectorization, so you can take advantage of the hardware that your computer has to run operations on multiple little bits of data simultaneously. And then it can eliminate some loop overhead, that's kind of similar to the vectorization topic actually, and introduce some optimizations as well. So NumPy will really help with the performance of any scripts that have a lot of numeric computation. Now, I would also like to mention CuPy, Cu from CUDA, Pi from Python. This is a drop-in replacement for NumPy that is GPU enabled. So this will really help if you have problems with high arithmetic intensity. And what I mean by that is that any operation to take data from your computer and transfer it to the memory of your GPU is going to take time. And so you don't want to be running things where you're not getting the real benefits of using a GPU. So a GPU is going to give you the most benefit, the greatest increase to performance, where you're running a lot of the same operations on little different bits of data. So this works well for things like matrix multiplication, and that's why GPUs work really well for machine learning packages in Python. But they're not exclusively for machine learning. So if you have an algorithm with high arithmetic intensity, meaning you're doing a lot of the same operations, then using a GPU may help. All right, so I have an example here of implementing NumPy. So this is a contrived example, certainly. It's just squaring some numbers. So what I'm doing here is initializing a fairly large list and a fairly large NumPy array. They're the same size here. In one case, I'm just using the range function in Python to create a range object, and in the other, I'm creating a NumPy array. And then I am running two corresponding operations here. On the list, I'm squaring each element in the list with a list comprehension. So for each x in data list, I am getting x squared and putting it into this list. And then in the second case here, I am using the NumPy array, and I'm just doing the square operation on it. Now the performance difference between this and this is actually quite significant. So the runtime of the second square operation, the latter operation that uses the NumPy array, has reduced by 94% on a fairly recent AMD EPYC processor. So this really shows that using these NumPy arrays, especially for large numeric computations, can really improve the performance of your Python scripts. Now you do have to be a little more careful when you're using NumPy. What I mean by that is when we're working with integers in Python, so the contents essentially of the range object here, Python integers will grow as long as you have the memory on your computer to enable them to grow. So you can't overflow an integer in native Python, but you certainly can in NumPy, where you have to treat it more like an integer in a lower level language like C or C++. So I specified a data type here as int64, and if I had done something like int32, this actually could have overflown. And so we'd get like a wrapping around of the integer values. So that is something that you need to be careful of when using explicit data types, which is far more common when working with NumPy, specifically because that helps with performance. So just something to be aware of when working with NumPy. Now another topic that I want to discuss is just-in-time compilers, and the example that I want to focus on here is Numba. So in the case of Numba and in the case of other just-in-time compilers, but let's focus on Numba here, you get a performance benefit through the compilation of numeric routines to machine code. So it is like a compiler for your Python code, even though Python is interpreted. And because of that, you can benefit from some of the features of lower level languages like static typing, vectorization. Some of these we also saw with NumPy, optimization. And in the case of Numba, there's also support for parallelism, so for ideally parallel problems. And just as with NumPy, there are options where you can run these resulting code on GPUs. So in this case, I would focus on the Numba CUDA package, which is maintained by NVIDIA. So as before, let's take a look at Numba and then look at an example of how Numba works in practice. So as we said, Numba compiles Python functions to machine code. The way this works is you put a decorator on a function in Python, and a decorator is essentially a function that takes another function as input. You can then tweak that function, how it works, and then return your results in the end. So we're putting our numeric calculation inside of another function. That function is one that's defined by Numba. And then Numba will compile that function to machine code, and when we call it, it will run the compiled version instead of the pure Python version. So there's actually what is called a dispatcher object that selects a compiled version based on the argument types. So that's to mesh the expectation of having defined argument types with the more flexible nature of pure Python, where you don't really need to specify types. And it will compile the function first as needed if it doesn't already exist in memory, or there's also an option to store it on disk. Now, Numba is going to work best with numeric types. You want to try and avoid what it calls object mode, which is when it's working with Python objects where it can't make these assumptions about the data types. and that is not going to confer the same performance benefit when you're in this object mode. So you really want to avoid using Python objects where you can, and there are some guidelines on how to do this on the Numba documentation and elsewhere. But essentially, Numba works well when you're working with numeric functions. So here is another example. Actually, the slow sum function is identical to the fast sum function, with the exception of this decorator here at JIT, just in time. So this is coming from Numba, and this is the decorator or the function that is going to take our function as input and then allow us to compile that to machine code and run that machine code instead of the pure Python function, which really confers the performance benefit. Now, when we run this the first time, so we run, first of all, slow sum, and then we run fast sum. When we run fast sum the first time, the runtime has decreased by 18% relative to slow sum. But I note that that is with the compilation overhead. So the first time we call this function, the just-in-time wrapper for this decorator, is going to say, hey, I don't have this in my memory yet as compiled to machine code, and so I'm going to compile it to machine code on your behalf. So a lot of the time that we spend on that first function call to fastsum is to compile fastsum to machine code. If I were to call this again, which is not shown here in this example, the runtime would decrease by more than 97% relative to standard Python. This is on the same CPU as before, a relatively recent AMD EPYC processor. So really, just by adding this single line here, we have had a significant improvement to our performance. Now, this again is a contrived example. You are probably not going to get this performance benefit for every algorithm, but certainly it's significant, and the effort to implement this is really quite small. We've added one line to import the just-in-time feature of Numba, and then we've added a single line to decorate this function, and we get a massive performance difference. So really, with NumPy and Numba, you can get significant improvements to the performance of your programs, your Python scripts, and you don't really have to invest a lot of time, particularly for Numba. So this is where I'd focus on improving your Python performance. Now, these, of course, are not going to cover every possible scenario where you want to improve the performance of your Python scripts. Not everything is as clean as the contrived example I had, where you're squaring some information or doing some simple mathematical operation, right? There are cases where there is additional complexity. Now, if you have a tightly coupled problem, or if you require high scalability, by that I mean you need to scale beyond a single system. You need to use distributed memory computation where you're scaling from one node on an HPC system to maybe 5 nodes on an HPC system. You really want to consider using NumPy for Pi, which is a language binding that enables you to use message passing interface features in Python. And if you have a problem that fits on a single system, a single node, a single computer with contiguous memory, and you don't require significant communication, consider using threading or multiprocessing. Threading, if you have something that is input or output heavy. This is largely historical because of Python's global interpreter lock, which only allows one thread of Python code to run at once, but you do get a performance benefit in that case if you are waiting on input or output. Although this has been relaxed recently in recent versions of Python, but still I think I would suggest only using threading in the case where you have input and output heavy work. Or multiprocessing, where you're running multiple processes at once. And those processes aren't going to share memory, but this is a very common operation for running multiple things at the same time in Python. Multiprocessing is a good way of doing that. So let's take a look at NumPy for Pi. NumPy for Pi provides Python bindings for message passing interface, NumPy. And so this is really useful if you want something highly scalable, where you're not confined to running on a single system. You can span across computers, across nodes. Now, one thing that I want to mention with MPI for Pi is that some methods have significant serialization overhead. So you really want to consider your data types and the methods you're using carefully. Serialization is the process of taking Python data structures, like Python objects, and flattening them into a single stream of binary that can be communicated among processes. So taking it from Python objects into, you can consider it like a stream of text, and then that text has to be reconstructed into Python objects on the other end. Now, send with a lowercase s is going to work with Python objects, while send with a capital S is going to work with NumPy arrays, which, as we saw earlier, have a clearly defined data type, and therefore we don't have to worry so much about like how large the objects are in memory. And Python can do some, or more realistically, MPI4Pi can do some optimization on actually transferring those data with the knowledge that they are contiguous in memory and that they have a defined data type. So my colleague Robben Migacz has an example script of how this works in practice, of solving the Laplace equation with MPI4Pi. But I will note, this example script includes the communication of Python objects, so those lowercase methods that are slower, not the NumPy arrays. So my challenge to you is, can you make it faster? And how? So I've returned to this slide. We've talked a bit about MPI4Pi. Of course, haven't gone in depth on how it actually works, but I think that's outside of the scope of this presentation. And I want to talk a little bit about multiprocessing now, so the right side of this screen. So the one thing I want you to take away from this presentation regarding multiprocessing is that communication is very slow with multiprocessing in Python. And this boils down to the way that the serialization and deserialization processes work. So when you have a Python object that you need to communicate over the network with MPI4Pi, you're going to go through this step of serialization first, and that is going to yield a sequence of binary opcodes. So Python is going to essentially deconstruct your object into a sequence of operations like get, put, empty list, tuple start, and then ultimately ending with stop, that are then used to reconstruct the Python object on the other end. So essentially you're running the operations that create the data structure that you need. So you're flattening your data structure, and then you're building it back up from the flattened version of it, which is a very resource-intensive process, especially if you're not doing much with that information afterward, which is actually what was happening in the case of that user I was working with. They had an operation that was quite quick to run. They wanted to scale it massively, but it turns out that transmitting the data over multiprocessing took far more time than actually running the operation. So serialization is a real consideration for Python performance, both in MPI4Pi and in multiprocessing. And that's really what I want you to take away as far as multiprocessing is concerned. Just have an awareness that communication can be quite slow with multiprocessing. There are some ways you can improve the performance, but in general, I would say to watch out for this. Okay, so what if you go to the trouble of optimizing your script with NumPy, with Numba? Maybe you've implemented MPI4Pi or multiprocessing and it's still too slow in the end. Well, in that case, I would recommend considering algorithmic changes or partial rewrites in low-level languages. So still using Python as your glue language and maybe as your interface and your tool for generating plots, which is quite nice in Python. But then if you have some calculation that's taking far too long, and it is Python that is the problem, the nature of the Python language that is the problem, then I would consider using a lower-level language and rewriting part of the script. Now this, of course, isn't always possible. There are cases where it's really the algorithm that is the problem, or the sheer scale of the data, and then you might need to reconsider how you're even approaching the problem. But if it is the language that is the issue, then there are mechanisms for writing your own low-level packages, just as we've seen with all of these other performance improving tools in languages like C, C++, Fortran, Rust. So I have some examples here, not necessarily that you need to completely understand, but just to show that this is possible, and in many cases it's not actually that much additional work to do this. So I have an example here that uses F2Py, Fortran 2 Python, which ships with NumPy actually, and it allows you to create a Python module from Fortran code. So I have a simple example here of a Fortran file, a modern Fortran file, where I'm defining a function add numbers that takes inputs A and B that are real numbers, and it yields, the syntax in Fortran is a little odd here, but add numbers, this is the output of the function. It yields A plus B. And I can compile this then using this F2Py tool into a module, and then import it into my Python script and run it here. So really not too difficult to use, provided, of course, that you can work with Fortran code. And you get all of the benefits of the low-level nature of this Fortran code, but you can use the Python language as glue on the right side. Now there's another example here of doing this in C, much the same add numbers function as before. It's a little more involved here. I'm just compiling this as a shared library with position independent code into some shared object file. It's a little more involved because you need to specify the argument and result types here for best results. But in the end, ultimately, we get the same result here, and we can run this lower level code, add numbers, where this function is coming from the C code over here, and get a result in our Python code. So again, using Python as glue. And I would say that getting started with these low-level packages, these low-level modules, is easier than ever with large language models, because you may already have your algorithm implemented in Python. It's just a matter of translating it. And even if you're not super familiar with Fortran or C, you can probably see with your knowledge of Python whether it looks correct from a glance, or you can interrogate the large language model and ask about certain features if you're not sure how something's working. So this is certainly not the first thing that I would do to try and improve Python performance, but it isn't off the table, especially with some of the newer large language model developments and the automation potential that really wasn't there in the past. So my takeaway here is continue using Python for structure, again as a glue language, but consider using other technologies for speed. Now, I do want to mention some recent developments in Python before I conclude here. So there are some recent performance-oriented Python features, and these quotations here are taken from a panel at Supercomputing 2025 on the future of Python on HPC systems, high-performance computing systems. And so there's a question about Python's built-in just-in-time compiler, which is a relatively new development, about whether it is going to take the place of Numba and similar tools. And the answer that the panelists gave, and an answer that I agree with, is that no, the internal just-in-time compiler is not going to take the place of Numba and friends, because the internal just-in-time compiler still has to produce standard compliant Python. It still has to be Python. It has to deal with different argument types and such. Whereas Numba can optimize some of that away. You can define a specific argument type for the input. As an example, there are other optimizations going on here as well. And there's a quotation here that the typical performance impact of enabling the built-in just-in-time compiler can range from 10% slower to 20% faster. So I guess a little bit better than random chance that your Python is going to run faster, but it really depends on the algorithm, and it may not actually confer any performance benefit. And 20% faster is certainly less than what we saw with the Numba example, where we cut the runtime for multiple calls of the same function ultimately by 97% relative to this standard Python. Now, the second quotation here relates to another feature, which is free-threaded Python. This is something I alluded to earlier with the disabling of the global interpreter lock, which will allow Python to run multiple things on multiple threads simultaneously. And the panelists here at this session said that this is not going to have as big an impact as it will for other areas of Python development. So Python is not just used for high performance computing, of course. It's broadly used across basically every discipline, and it's often used, for example, by web developers. And the panelists here were of the opinion that the free-threaded Python, while potentially useful in scientific computing, is going to be largely useful for developers in other areas. So like web development, where you could have a web server that needs to respond to multiple requests simultaneously. Now, that's not to say that scientific high-performance Python is not going to benefit from the free-threaded Python implementations, but it's not going to confer a lot of the same benefits that you would get from Numba or from designing something that is scalable with MPI for Pi, for example. So it is something to watch for the future, but maybe not something to focus on, at least in the near term, for improving the performance of scientific Python scripts. So I come back to this question, the same question that I opened with: why should we care about Python performance, and isn't performance-conscious Python an oxymoron? Well, no. I think that Python is growing in popularity among high-performance computing audiences, especially for new users just entering the world of HPC without maybe some background in lower-level programming languages. And as we've seen throughout this presentation, there are mechanisms for dramatically improving the performance of Python scripts. And so you don't want to ignore those mechanisms for improving the performance, especially for a tool that is as easy to pick up relative to low-level languages as Python. So a lot of new users are coming into the world of Python because it is easy to use. But it's not just easy to use. It's easy to use, and it provides mechanisms for really scalable, performant software. So I certainly care about Python performance, and I think it's worth considering Python performance in your own software. So I end here with my own opinion. Python is a performance-oriented language. This is one that I share with a panelist at, again, this Future of Python on HPC Systems panel from SC25. Python is a performance-oriented language because you can consider the performance of your Python scripts, even though that might not be necessarily the default behavior of most Python developers. So there are mechanisms for improving the performance of Python. And if you have any questions at all about this presentation, I'd be happy to help. You can email us at helpdesk@chpc.utah.edu. My colleagues and I watch this email address during business hours, and we're happy to help with your Python-related questions. And I do want to acknowledge the support of my colleagues in the development of this presentation, and also some concepts that I took from San Diego Supercomputer Center presentations on Python for high-performance computing. Thank you.